Yeah, good evening all. Okay, we are talking about the data structure using Java. The subject is data structure using Java. Just a minute to share you the notes. Yeah. So as part of the subject, we started our course from the topics block one, lists and stacks, and block two, queues and trees, and block three, hashing and heaping. So we started our discussion with the hashing yesterday. So we are completed hashing. Then we are supposed to discuss about the types of sortings. Types of sortings. So this is our topic today. Types of sorting is our topic. Coming to sorting now. As part of the queues, we completed circular queue, double-ended queue. We completed. Now, if you can revise this textbook, you can revise this textbook for these queues functions, which are from the util package, and you can download this package from the Oracle website. Any API you can download. Can be Java 6 or 8, any API you can download. You can find this util package. Now, these are the methods we discussed in the queue data structure. Use data structure. Now, these are all the programs you try to execute in your local computer. The implementation by using Java, you can execute in your local computer. And circular queue is also we discussed. Then double-ended queue. This is a double-ended queue. In that, these are the operations: add back, add front, delete back, delete front, get back, get front, empty, full. These are all the operations can be performed in the double-ended queue. That is, we can call as a DQ also. Can call as DQ also. Then after we discussed even tree data structure, as part of the tree data structure, the what is the general tree definition and abstract data type, ADT, and what are the binary trees and ABL trees. Binary trees and ABL trees. These are the tree data structure functions we can call. The root function, parent function, children function, and is internal, is external, is root, size, is empty, iterator. These are all functions. So what a root function does is, root function returns the position of the root of the tree. And if it does not have any, then it returns null in case of the empty root. Then parent returns the position of the parent of P, and null if P is the root. So these are the functions. Binary trees. Then just go through all these concepts once again and try to execute all these programs in your local computer. Now we are in the heap where so we are in the hash function. So we are using the hash function. So what is an hash function we discussed yesterday? The hash function is applied on a key, so where it produces an integer value, where it produces an integer value. So that can be used as an address of the each hash table. So they can use the same hash function for accessing the data from the hash table. So in this types of hash function, we have used the division method we use a mid square method, and we use a digit folding method. And we also even discussed collision. That state chaining we discussed, and that implementation of the state chaining in the Java program. Then hash table without linked list also we discussed the linear probing and quadratic probing and double hashing. Then after this, hash table with worst case scenarios. Hash table with worst case scenarios. So here the hash table which we examine, so it is have all of the properties, but it's an appropriate hash functions. We can expect the big of 1 cost on average for insertions. It is for insertion, removes, and for searching also. For separate chaining, assuming a load factor of 1, there is one version of the classic balls and pins problem. Classic balls and pins problem. So next to co-creation also, it applied the idea of the multiple choice and relocation together and the guarantee because of 1 in worst case lookup time. So whereas in multiple choices, we can give 2 choices, H1 of that key and H2 of that key. Relocation, it may happen that, 2 keys. It happen that 2 keys. So it pushes the other eggs or young out of the nest when it hatches. So this is a kind of example. It's resolved by mitigating the foobar. So the insertion is expected because of 1 and deletion is also because of 1 in the worst case. So it requires inspection of just two locations in the hash table. So this is an input. So hash function here, we can take h1 of key, the key percentile. This is a table with different iterations and with the different hash key values. Now, the coming to complexity, the other types of hash tables, the worst case complexity is big of n, and assuming the hash function disperse the keys evenly, the expected time complexity is constant. So when it comes to the lookup a key, that is at the home bucket, B is located based on the hash of key, that is K. The home bucket stores K. So otherwise, it can examine the other buckets in the neighborhood that has B as their home bucket. So this is for lookup. Then for the complexity, lookup examines at the host most of the edge buckets, which is constant. So that has a worst case complexity of big of 1. When it comes to removal, the relevant bucket is located the same way as lookup is performed. The key is removed by clearing the bucket. So any meta info about neighboring buckets, so it must be updated as well. So hopscotch is hashing does not require a special deleter making with marking and as other open addressing techniques. Other address. So complexity here. Now rehashing works as usual. A larger array is allocated and each element is removed from the original array and inserted in the new array. Like this, if you take an array, this is array. So here says the rehashing works. A large array is allocated. Each element is removed from the original array. So let us say this is an original array. Let us say this is having these elements. This is having these elements. Is having these elements. And these original elements can be moved to the these original element moved to the new array. This is new array. It's a new array. These are all elements can be moved to the new array. So this is called rehashing. So when we're keeping track of the home buckets, to quickly find the suitable candidate for swapping during the insertion, the implementation provided in the that original paper. So each bucket has a bitmap of h bits, and between the bitmap of bucket B is set if and only if bucket of B plus D is occupied by a key that has B as its input. So each bucket has a linked list of reference to other buckets. The linked list in bucket B that linked list in the bucket B has a room bucket. So the large neighborhood, this may be more memory efficient representations. On the other hand, it introduces some indirection which could impact performance. Then coming to universal hashing and extendable hashing. Universal hashing and extendable hashing. The performance of the hash tables generally depend on the hash function having two fundamental properties. The hash function must be computable in constant time, that is independent of the number of items in the hash table. So the hash function must distribute its items uniformly among the array slots. So in particular, if the hash function is poor, then all bets are off. All bets are off. And the cost per operation, it can be linear. So that universal hash function, which allows to choose the hash function randomly in such a way that condition 2 is satisfied. So the strong motivation for the use of universal hash function is to provide the theoretical justification for the assumptions used in the classic hash table analysis. So these functions can also be used in applications and that require a high level of robustness, in which worst case are even substantial degradable. So universal hash function, a family edge of hash function is universal if for any x is y, the number of hash functions in H4, which h of x is equals to h of y. So the analysis of the cuckoo hash function requires an big of log n, which universal hash function. So after that, many evictions, so we give up and rehash. So to design a simple universal hash function, it will assume first that that are mapping very large integers into small integers ranging from 0 to some variable. So prime larger than the largest input key. So the use of universal hash function for separate chaining or hopscotch hashing would be sufficient to meet the assumptions used in the analysis of those data structures. However, it is not sufficient to meet the assumptions used in the analysis of those data structures. So it requires a stronger notion of independence. In cuckoo hashing, if there is a vacant location, there is not, and a different item is now involved in looking for a vacant location. So this represents until that find the vacant location or decide no to rehash. So universal hash functions exist for strings also. First, choose any prime which larger than m and larger than the largest character code. Then use a standard string hash function, choosing the multiplier randomly between 1 and p. So 1 and returning an intermediate hash value between 0 and p, 1 inclusive. And finally, apply universal hash function to generate the final hash value between 0 and m. Extendable hash function, hashing, which come into picture where the amount of data is too large to fit in main memory. The main consideration than in the number of disk access required to retrieve data. So before we assume that at any point we have n records to store, the value of n changes over time. So furthermore, at most m records fit in one disk block, we'll use m is equals to 4. So if either probing hash function or separate chaining hash hashing is used. The major problems that collisions would cause several blocks to be examined during a search, even for a well-distributed hash table. Furthermore, when the table gets too full, an extremely expensive rehashing step must be performed, which requires N disk access. A clever alternative known as extendable hashing also has search to be performed in two disk accesses. Insertion also require few disk accesses. We recall from chapter previous sections that a binary tree has a depth. So as the m increases, the depth of a binary tree decreases. So that could, in theory, choose m to be so large that the depth of binary tree would be 1. The any search after the first would take one disk access. So the root node could be stored in main memory. The problem with this strategy is that the branching factor is too so high that it would take considerable processing to determine the data was in. So if the time to perform this step would be reduced, then the practical scheme is exactly the strategy used extendable hashing. So if any data consists of several 6-bit integers, and it shows an extendable hashing scheme for these data. So root of the tree contains 4 pointers determined by the leading 2 bits of the data. Each leaf has up to m is equal to 4 elements. It happens that in each leaf, the first 2 bits are identical. This is indicated. So by the number in parentheses to be more formal, so D will represent the number of bits used by the root, which is sometimes known as the directory. The number of entries in the directory is thus 2D. So DL is the number of leading bits that all the elements of some leaf L have in common. So it depends on the particular leaf. Suppose that if it wants to insert the key, so 100, 100, so that would go into the third leaf. But as third leaf is already full, there is no room. So then it split this leaf into 2 leaves, which are determined by the first 3 bits. So this require increasing the directory size to 3. So these changes reflected in the next phase. Now coming to the priority queues. In the priority queues, this will cover the binary heaps or heaps, the applications and types of heaps. These are. The objective of this chapter is will be understand priority queues. It explains how to implement binary heap, describes the application of heaps, describes the various types of heaps. And the priority queues, it is talking about the priority queue is new abstract data type, which is collection of prioritized objects as elements that allow arbitrary elements insertion and allows the removal of the element that has first priority. So when an element is added to a priority queue, the user designates its priority by providing an associated key. So the element with the minimal key will be the next to be removed from the queues. So which has any element with the key 1 will be given priority over an element with key 2. So although it is quite common for priorities to be expressed numerically, so any Java object may be used as a key. Here any Java object here means you can take any physical entity is an object as a key. As long as there exists means to compare any two instances A and B. Here instances means it is also an object in a way that defines the natural order of the keys. With such generality, applications may develop their own notion of priority for each element. So different financial analysts may assign different ratings. So to a particular asset, share of stock. A priority queue is a data structure that allows at least the two operations. As per our discussion in the earlier class, the priority queue functions, these are all. Then heaping, also we discussed in the previous class. The applications and types of heap, this also we covered. Now we are talking about this sorting. In this sorting, the discuss it covers insertion sort, shell sort, merge sort, and quick sort. So sorting an array of elements is a best practice. It's a kind of good practice to sorting an array of elements. To that assumes that array contains only integers. Array contains only integers. And more general objects, that entire sort can be done in main memory. The entire sorting can be done in main memory. So the number of elements is relatively small, that is less than a few million. It's charts that cannot be performed main memory and must be done on disk or tape are also quite important. So this type of sorting is known as external, and investigation of internal sorting will show that. So there are several easy algorithms to sort in. There's B of N2. There's insertion sort. There's an algorithm for shell sort. So the algorithm describes all interchangeable. Each will be passed an array contain the elements. So that assume all array positions which contains data to be sorted. Now, first one, insertion sort. The insertion sort technique that assumes that first element in the list is already sorted and that they begin the second element. The second element is compared with the first and swapped if not in order. So this process is repeated for all the subsequent elements. So in general, the insertion sort technique compares each element with all of its previous elements and sorts the element to place it in its proper position. As already mentioned, the insertion sort technique is more feasible for smaller set of data and the arrays with a small number of elements that can be sorted using efficiently insertion sort. Insertion sort is especially useful in sorting linked list data structure. As we know that linked list have pointers pointing to its next element, that is single linked list, on previous element, the double linked list. So this makes it easier to keep track of the previous and next elements and is easier to use insertion sort for sorting linked list. However, sorting will take a lot of time if the data items are more. And sorting an array using insertion sort, the original array is as this original array is 10, 2, 6, 15, 4, 1. Now for each pass, we compare the current element to all its previous elements. So in the first pass, so current element to the previous elements, compare second element to the first element before it, and so on. See here, when compare the first element with the previous element, second element with the previous element, that is 2 to 10. So 2 is smaller than 10. So 2 will be moved to the first and 10 is moved to the next. And compare the third element to all elements before 10 sort. So again, 6 and 10 will be compared and that will be interchanged. So this we got the latest updated array and compare the fourth element to all. Then compare to 15 and 10. So we got the updated array. So finally, we get the sorted arrays 1, 2, 4, 6, 10, 15. So this is a sorted array. This is a sorted array. So here we have taken the arrays here. So before insertion sort and sorting array using insertion. So after analyzing the insertion chart, in the nested loops, each of which can take n iterations, the insertion chart is big of n2. So input and reverse order can achieve this bound. So lower bound for simple sorting algorithms. In simple sorting algorithms, such as insertions, an inversion in an array of numbers is defined as any ordered pair having the property that I less than j. So that is exactly the number of swaps that needed to be performed by insertions. It's always the case because swapping to adjacent elements that are out of place remove exactly one inversion. And a sorted array has no inversions. Since there is a big of n other work involved in the algorithm. So the running time of insertion sort is big of I plus n, where I is the number of inversions in the original array. So insertion sort runs in linear time. The number of inversions is big of n. So we can compute precise bounds on the average running time of insertion sort by computing the average number of inversions in a permutation. So defining average is a difficult proposition. So that will assume that there are no duplicate elements If allow duplicates, it is not even clear what the average number of duplicates is. So using these assumptions, that can assume that the input is some permutation of the first n integers. Saying that all are equally likely, and with these assumptions that have the theorem, so that is rule 1, 2, like this. The rule 1 says that the average number of inversions in an array of n distinct elements is n of n1 by 4. The rule 2 says any algorithm that sorts by exchanging adjacent elements requires n2 time on average into time and average. So next type of sorting technique is shell sort. Shell sort, it is named after its the author Donald Shell. He was one of the first algorithms to break the quadratic time barrier. So it was not until several years after its initial discovery that a subquadratic time bound was proven. So as suggested in the previous section, it works by comparing elements that are distinct. The distance between comparisons decrease as the algorithm runs until the last phase, in which adjacent elements are compared. So for this reason, shell sort is sometimes referred to as a diminishing increment sort. So who is the author of this shell sorting technique is Donald Shell. So it describes the shell sort algorithm. Which know what it is trying to implement. The shell sort is based on the insertion sorting algorithm. Shell sort is based on the insertion sort algorithm. It and it belongs to the group of very efficient algorithms. Just take an example. So example says, uh, the shell sort is based on the insertion sorting algorithm, and it belongs to the group of very efficient algorithms. So the algorithm breaks an original set into smaller subsets, and then each of those subsets is sorted using the insertion sort. So it makes the subset is not straightforward actually. It doesn't choose neighboring elements to form subset. So rather shell sort use the so-called intervals, or we can call gap. So for subset creation, what it uses, it uses the intervals or gap to create the subset. So here the gap one, it means that one subset will contain the elements that are first position apart. So the algorithm sorts the elements that are far away from each other. The gap becomes smaller and closer elements are compared. And this way, some elements that are not in a correct position can be positioned faster than if we made the subset out of the neighboring elements. So example here, the 9 elements are there, 41, 50, 92, 5. 65, 19, 32, 43, 8. So after sorting the each of the subsets in the first iteration, the list is like this. So 5, 15, 8, 32, 43, 19. So that don't have sorted list yet. The elements are now closer to desired positions. So finally, it requires one more sort of the increment of one, and it's actually a basic insertion sort. It's a basic insertion sort. So the number of shifting operations that need to perform to sort a list is now smaller than it would be the case if didn't do the first iteration. So choosing the gap sequence, as mentioned, the shell sort has a unique way of choosing the gap sequences. It's a difficult task as it would be carefully not to choose too few or too many gaps. So in more details, so after all iterations is a final sorting of the elements. So this can be implemented by using the program. Here the class name is shell sort. Class name is shell sort. The array name is myArray. And we are finding the length of the myArray here. And for that, they applied the for loop, the outer for loop, and the inner for loop. And after that, we are adding to the variable time, and j is declared with empty. And after that, again, for loop is written, and that can be added to the myArray. And after that, the temp can be stored back to the myArray. So it's a main function. Here the myArrays, these are the elements of the myArray. And the object is created with the shell sort. This is the class name. So that can be called, shell sort function can be called with a myArray values. And that can be displayed by using this function. So again, here length will be checked again. For loop is written, and that myArray will be displayed here. So this is the shell sort implementation. Now, one more sorting technique is merge sort. It is one of the most efficient sorting algorithm, and it works on the principle of divide and conquer. Merge sort repeatedly breaks down a list to several sublists, so until each sublist consists of a single element, and merging those sublists in a manner that results into a sorted list. The fundamental operation in this algorithm is merging two sorted lists. The lists are sorted. This can be done in one pass through the input. The output is put in a third list. The basic merging algorithm takes two inputs arrays A and B and output array C. And three counters, so ACTR and BCTR and CCTR, which are initially set to the beginning of their respective arrays. The smaller the ACTR is occupied to the next sentence. So appropriate counters are advanced when either input list is exhausted, the remainder of the other list is copied to. An example of the merge routine works is provided for the Example input. The top-down merge sort approach is a methodology which uses recursion mechanism. It starts at the top and proceeds downwards with each recursive turn, asking the same question, what is required to be done to sort them? Now having the answer as split the array into two, make a recursive call and merge the results so until one gets to the bottom of the array tree. Your example to discuss here is to understand the approach better. So divide the unsorted list into n sublists, each comprising one element. A list of one element is suppose sorting. So top-down implementation repeatedly merge sublists to produce newly sorted sublists until there is only one sublist remaining. This will be sorted list. So merging of two lists done as follows. The first element of both lists is compared. If sorting is ascending order, the smaller element among two becomes a new element of the sorted list. So this procedure is repeated until both the smaller sublists are empty and the newly combined sublist covers all the elements of both the sublists. The bottom-up merge sort implementation, the bottom-up merge sort approach uses iterative methodology. It starts with a single element array and combines two adjacent elements and combine two adjacent elements and also sorting the two at the same time. So the combined sorted arrays are again combined and sorted with each other until one single unit of sorted arrays achieved. So to understand the concept of the example with iteration 1, here the pairs of two, the array size 1, these are the 0 to 7, that is 8 values. So merge the pair of arrays size 4. There it goes. So for implementation of merge sort, so the merge sort is a classic example for the technique used to analyze recursive routines. So you have a a recurrence relation for the running time, and that will assume that n is a power of 2, so that we always split into even halves. So for n is equal to 1, the time to merge sort is constant. So which we denote by 1. Otherwise, the time to merge sort n numbers is equal to the. So the next type of sorting technique is quick sort. Next type of sorting technique is quick sort. The quick sort uses divide and conquer to gain the same advantages as merge sort. While they're not using additional storage, as a trade-off, however, it is possible that the list may not be divided in half. When this happens, we will see that performance is diminished. The quick sort first selects a value which is called the pivot value. Although there are many different ways to choose the pivot value. So that will simply use the first item in the A list. So the role of the pivot value is to assist the splitting the list. The actual position where the pivot value belongs to the final sorted list, so which commonly called split point. So that will be used to divide the list for subsequent calls to the quicksort. So that shows the example which shows that 54 will serve as first pivot value, since which I've looked at the few times already, that 54 will eventually end up in the position currently holding 31. The partitioning process will happen next. So it will find the split point and at the same time move other items to the appropriate side of the list, either less than or greater than the pivot value. The partitioning begins by locating two position markers. So that call them left mark and right mark. The beginning and end of the remaining items in the list. That is that begin incrementing left mark until that locate a value that is greater than the pivot value. It then decrement the right mark until it find a value that is less than the pivot value. Now at this point that I have discovered two items that are out of place, which with respect to the several split points. Here example, it occurs 93 and 20. 93 and 20. So that can exchange these two items and then repeat the process again. So at that point where right mark becomes less than the left mark. The position of right mark is now the split point. The pivot value can be exchanged with the contents of the split point, and the pivot value is now in the place in additional. All these items at the left of the split point are less than the pivot value. So all the items to the right of the split point are greater than the pivot value. So this one, if you take a 54 here, the rightmost value are all greater than this pivot value, and the leftmost values are less than the pivot value. So now this list can now be divided at the split point, and the quicksort can be invoked recursively on the two halves. So this is one half and this is one half, and this is another half. This is the pivot value. So the quicksort function is an active code. One invokes a recursive function, that is quicksort helper. The quicksort helper begins with the same base case as the merge sort. So if the length of the list is less than or equal to 1, it is already sorted. If it is greater, then it can be partitioned and recursively sorted. So the partition function implements the process described earlier. So which analysis the quicksort is in worst case running time. If you consider the worst case running time, so the quicksort always has the most unbalanced partitions possibility. So that is the original call takes. So n time for constant C, the recursive call on n minus 1. So in minus 1. So one element takes the C of n minus 1, the left parenthesis n minus 1, the right parenthesis time. Now coming to the best case running time. Best case running time. The quicksort best case occurs when the partitions are as evenly balanced as possible. So the sizes either are equal or are within a one of each other. The former case occurs if the subarray has an odd either are equal within one each, or the number of elements on the pivot as is right in the middle after the partition. So that we have seen the example in the earlier. So each partition has n minus 1 by 2. The two left parentheses, n minus 1, right parenthesis, that is later occurs. So average case running time shows that average case so the best case running time, worst case running time, average case running time. So in average case running time, the pivot ends up somewhere here, as I'm showing the diagram. Showing the diagram. So next in the randomized quick sort. Suppose the worst enemy has given you any array to sort with quick sort, knowing that you always choose the rightmost element in each array, subarray as pivot, and has arranged the arrays so that always get the worst case fit. So we could not necessarily choose the rightmost element in each subarray at the pivot as a pivot. Instead, randomly choose an element in the subarray and use that element as the pivot. The partition function assumes that the pivot is the rightmost position of the subarray. So just swap the element that you choose as a pivot with the rightmost element and then partition as before. So unless your enemies knows how you choose a random location in subarray, so in fact, with a little more effort, that can improve the chance of getting a split that's at worst 3 to 1. So randomly choose not one, but three elements from the subarray and take median of the three as a pivot, swapping it with the rightmost element by the median. That means the element of three whose value is in the middle. So, but if you choose the median of three randomly chosen element as the pivot, so that will have this 68.75% chance, that's 11 by 16, which are getting to 3 to 1 split or better. One split or better. So can that we choose the five elements at random and take the median as a pivot, the chance worst case 3 to 1 split improve about 79.3%. That is 203 by 256. And remaining the seven randomly chosen elements, it is 85.8%. And the median of 11, it is 93.1%. So it doesn't necessarily pay to choose a larger number of elements at random and take the median, but for the time spent doing so could counteract the benefit of getting good splits almost all the time. So next topic would be discussing searching and sorting. The next level of searching and sorting, that a heap sort, decision trees, and bucket sort, radix sort, and these are all. In tomorrow class, we'll discuss that.